Welcome to Module 1 of our course on Database Management Systems. In this first module, we will lay the foundation for your understanding of what a database is, why database management systems are essential in the modern world, and how different models and design processes shape the way we store, manage, and use data. We will begin by looking at the user interface and user views of a database, then move into the critical concept of data independence, which allows us to separate the way data is stored from the way it is accessed. After that, we'll explore the major data models that have shaped database technology: relational, hierarchical, network, and object-oriented. Once we have those foundations, we'll step into the 3 stages of database design: conceptual, logical, and physical. We'll examine normalization, a process for organizing data efficiently, before touching on query languages and query optimization, which ensure we can retrieve data quickly and accurately. Finally, we'll cover security, integrity, and concurrency protocols, which protect data and ensure reliable multi-user access. 1.1 Understanding the user interface in DBMS. When we talk about a database user interface, we mean the point of interaction between the user and the database system. This can be a graphical user interface, GUI, where forms, buttons, and menus allow users to navigate and retrieve data. A command line interface, CLI, where users type queries directly, often in SQL. A web-based interface integrated into applications, such as an e-commerce site admin panel. An API interface where other programs interact with the database without human intervention. The choice of interface often depends on the type of users, the complexity of tasks, the level of access and security required. For example, a database administrator may prefer a CLI for precision, while a salesperson might use a GUI form to quickly pull up customer information. 1.2 User View. The user view is the subset of the database that a particular user needs to see. A database might contain a massive amount of data, but not every user needs, or should have, access to all of it. Think of a university database. A student might see only their own grades, timetable, and fees. A lecturer might see class lists and grades for courses they teach. An administrator might see all academic records and financial data. Why user views matter? They improve security by restricting access. They make the system easier to use. Users don't need to navigate irrelevant data. They allow customization of data presentation. 1.3 Data independence. Data independence means we can change how data is stored without affecting how it is accessed, and vice versa. There are 2 types. Physical data independence, the ability to change physical storage, such as moving from magnetic disks to SSDs, without rewriting applications. Logical data independence, the ability to change the logical structure of the database, adding a new column, splitting a table, without changing the applications that use the data. Without data independence, every change to the database's structure would require rewriting application code, leading to high cost and complexity. 1.4 The 3 data models. Relational model. The most common model today. Data is stored in tables, relations, made up of rows, tuples, and columns, attributes. Relationships between tables are established through keys, primary keys for unique identification and foreign keys for links between tables. Example, in a retail system, a customer's table can link to an order's table via customer ID. Hierarchical model. Data is organized in a tree-like structure. Each record has a single parent but can have many children. This model is good for representing structured data like organizational charts or file systems. Example, in a company hierarchy, each employee reports to one manager, but that manager may have multiple subordinates. Network model. Data is organized as records connected by links, forming a graph. This model allows many-to-many relationships directly without the need for junction tables. Example, a student's record could directly link to multiple courses, and each course could link to multiple students. Object-oriented model. Combines database capabilities with object-oriented programming. Data is stored as objects, with both state, attributes, and behavior, methods. Suitable for complex data such as multimedia, CAD designs, or engineering simulations. 1.5 Database design stages. Designing a database is like building a house. You plan before construction. 1. Conceptual design. Focuses on what the system will contain, not how it will be implemented. Uses entity relationship (ER) diagrams to define entities, attributes, and relationships. 2. Logical design. Converts the conceptual model into a logical schema. Decides on data types, relationships, and constraints. Still independent of physical storage considerations. 3. Physical design. Decides how the data will be stored on hardware. Includes indexing strategies, partitioning, and storage optimization. 1.6 Normalization. Normalization is the process of organizing data to reduce redundancy and improve integrity. First normal form, 1NF, eliminate repeating groups, ensure each field contains only atomic values. Second normal form, 2NF, eliminate partial dependencies on a composite key. Third normal form, 3NF, remove transitive dependencies. Benefits: less data duplication, easier updates, improved consistency. However, overnormalization can lead to performance issues, so sometimes a controlled level of denormalization is used for speed. 1.7 Query languages. Query languages are tools for interacting with databases. Declarative languages like SQL allow you to specify what data you want, not how to get it. Procedural languages like PL/SQL include step-by-step instructions. Examples of SQL operations: retrieving data with select, inserting data with insert, updating data with update, deleting data with delete. 1.8 Query optimization. Query optimization ensures that database queries run efficiently. Optimization can involve choosing the best indexes, rewriting queries for efficiency, using query planners and execution plans. Example: a poorly written query that joins large tables unnecessarily can be rewritten to filter data before joining. 1.9 Security, integrity, and concurrency protocols. Security controls access through authentication and authorization. Uses permissions, roles, and encryption. Integrity ensures data accuracy and consistency. Enforced through constraints like primary keys, foreign keys, and unique constraints. Concurrency ensures multiple users can work with the database at the same time without conflicts. Achieved through locking, transaction isolation levels, and deadlock prevention.